We have lasers, drones, and heavy machinery, yet the overall productivity of the construction industry has stalled out for decades. The tools have evolved, but the speed of putting a building together hasn't. If you want to know why a timeline is slipping, you usually have to look at the rebar. The installation of these steel reinforcement bars is a highly manual process that dictates the pace of the entire structural build. This process breaks down into 4 distinct physical stages, as seen in these photos: cutting the steel, transporting it across the site, positioning it into place, and finally fixing it together. That last step, fixing, is where the real friction happens. Workers have to manually tie every single intersection of steel with soft iron wire. A slight misalignment weakens the concrete structure, so the work has to be exact. Because this phase is so repetitive and physically demanding, project schedules regularly fall apart here. Standard planning timelines rarely account for the specific physical toll and exact duration required to manually tie thousands of intersections on a real, constrained site. Historically, the industry has relied on something called work sampling. This means managers walking the site with a clipboard and a stopwatch, trying to categorize work into direct tasks, indirect support, or wasted time. But that method is incredibly labor-intensive. It forces planners to estimate future schedules based on raw volume, guessing how many labor hours it will take to reinforce a certain square footage or weight of concrete. This shows what volume estimates ignore: geometric complexity. A wide-open flat slab is easy to reinforce, but take that same square footage, add columns, elevator shafts, and tight edges, and you restrict worker movement. The physical space dictates work speed. If you only measure the volume of materials, your schedule is a guess. To create an accurate timeline, you have to map the complexity of the physical space against the time it takes humans to maneuver through it. Replacing the clipboard requires a way to measure labor automatically. Recently, researchers have started deploying computer vision, using cameras to interpret human actions and track on-site productivity without interrupting the work. The AI maps specific anatomical nodes to track human posture frame by frame without wearable sensors. By analyzing trunk and limb angles, the system classifies the exact task. An upright posture indicates transporting materials, while a bent spine flags labor-intensive fixing work. When tested on over 1,900 labor hours in active construction environments, this posture-based classification model hit a 97% accuracy rate. Because the cameras track where the workers are standing while they bend over to tie the rebar, the system generates a highly precise data map. It shows exactly how many as-performed labor hours were spent on every single square meter of the site. With the actual labor hours recorded, that data can be compared against the as-designed digital blueprints, specifically the 3D Building Information Models, or BIM, which contain all the structural geometry. To compare the two, researchers overlay a digital grid onto the blueprint. They chop the construction site into 5 by 5 meter squares, calculating a specific complexity score for each cell based on how many walls, columns, and tight edges are clustered inside it. These heat maps show the results. On the left is actual activity duration. On the right, mathematical complexity extracted from the blueprint. Notice the dark red squares. The areas flagged as highly complex match almost perfectly with where workers spent the most time. This proves that a 3D blueprint holds the exact coordinates of future delays. By scoring the spatial complexity in advance, planners can predict where the bottlenecks will happen before a single truck of concrete is even ordered. For managers on the ground, the takeaway is to stop building schedules based purely on the raw tonnage of steel. Instead, they can run their 3D models through a spatial analysis to flag the high-complexity red zones early in the planning phase. Once those heavily constrained areas are identified, project leads can adjust their strategy. They can assign more time in the schedule for those specific grid squares, or route their most experienced crews to handle the trickiest intersections. This data also offers a massive ergonomic advantage. Because the computer vision specifically tracks body posture, site managers know exactly which zones will force workers into prolonged bent-over positions. Workers assigned to those areas face a much higher risk of musculoskeletal injuries. Managers can use this grid data to mandate frequent task rotations, moving crews between heavy fixing zones and lighter transport duties to reduce physical strain. This approach uses AI to quantify the physical difficulty of labor, creating schedules that respect the reality of the work and the humans performing it. To learn more about how data is solving the physical bottlenecks in modern industries, hit subscribe and let us know what process we should analyze next.